Possibly one of the most confusing, yet useful ideas for problem solving in coding interviews is the monotonic stack. In this video, we're going to show you an example and summarize it, so make sure to stick to the end. The monotonic stack is, as you might have guessed, a stack, which uses some greedy logic to keep the elements in the stack orderly after each new element is put onto the stack. What kind of order are we talking about? It could be either monotonically increasing, which means the elements either increase or stay the same as we go left to right, or monotonically decreasing, which means that it either decreases or stays the same as we go left to right. Let's look at an example. Given the heights of 5 people, find the height value of the person with the next largest height. If there is no larger height, store -1. Let's think about the brute force solution first. For each height, iterate through the rest of the array to find out the next greater height. The time complexity would be O of n squared, but do we really need to loop through the entire rest of the array? We're going to iterate from right to left and use a monotonic stack to keep the higher people on your right. In this case, we're going to be maintaining a monotonically decreasing stack. Every time we put an element into the stack, we still want to make sure that the stack is monotonically decreasing. We have 2, 1, 2, 4, and 3. So, of course, once again, we're going to be moving from right to left, and we're going to have our stack which maintains the greater values than the current height. So for example, if we were to deal with this 3 here, and this 3 pertains to this person in the blue on the right here, we see that the stack is empty. If the stack is empty, that basically means that, okay, nothing is greater than 3 so far. So what that means is we can just assign this value -1, which means that the greatest height so far, or the greatest height on the right side of this person, is nothing, meaning it's -1. So in that case, let's just put the 3 into our monotonic stack. And remember, this is a decreasing monotonic stack. Next, let's deal with this number 4. And this 4 pertains to this red person here. And so if we were trying to put in this 4 here, we're trying to maintain a monotonically decreasing stack, meaning the smaller elements are at the top and the larger elements are at the bottom. If we were trying to put this 4 into here, that would break our invariant. So what we need to do is we need to take this 3 out, and then finally, we see that the stack is empty, meaning that nothing is greater than this 4 on the right side. So put the -1 here, meaning that nothing to the right is greater than this 4. So let's put this 4 into our monotonic stack. Next, let's deal with this 2 here, which pertains to this green person. Obviously, we can see that the answer for this is going to be 4, because the person of height 4 is greater than this person of height 2. And so what we can do is we realize, okay, 4 is the top of our stack, which means that this is the next greatest element greater than this 2. So we can easily just put the 4 here, which is our answer, and we can put 2 into our monotonic stack. Because then when we deal with the next person, which is of person height 1, we can see, okay, the person at the top of the stack is the first person that's greater than this, right? That's why we're keeping these elements in here in a monotonically decreasing order. So let's put this element into here, and we see that the top element is a 2, so that's our answer for 2. And we maintain our invariant, which is just going to be decreasing, so we can just put the 1 into our monotonic stack. And finally, let's deal with this yellow person here, which is of height 2. We want to put this into our stack, but we want to find the first person that's strictly greater than this 2, right? So what we're going to do is we want to maintain the invariant. So we take out the 1, okay, but this is still not decreasing, strictly decreasing. So we need to take this 2 out. And then finally, we see that we can successfully put the 4 or this 2 inside, and the top element is going to be the 4, meaning that the answer in this case is going to be 4. So we put the 2 in, and that's our final stack. We're done here, and we see that we finished all the items, and this is the answer for our specific case. So what does the code look like for the next greater element problem? What our function does is takes in an array of heights, and what we're going to do is create an array of integers as well as a monotonic stack. This could just be implemented as a regular stack. We're going to loop through the elements from the right side all the way to the left side. And what we're going to say is while our stack is not empty and the element at the top of the stack is less than or equal to the current height that we want to insert, then pop the stack. Next, what we want to do is check if the current stack is empty. If it is empty, then we just say that the answer is -1 for the current element because nothing is greater than it. And otherwise, the element at the top of the stack is going to be the answer for the ith element. Then simply, we want to push our element into the stack because we know it's going to maintain the invariant. Finally, return the answer. The reason that all of this works is because the monotonic stack stores both the position and magnitude of the values. The position is stored by the order in the stack, and the magnitude is stored by popping stuff off of the stack. And that's exactly why we're able to achieve this O of n time complexity. Otherwise, we would have an O of n squared. That's it for the monotonic stack. If you like this video, like, comment, and subscribe.